Okay, good morning, everybody. I just have some brief announcements for today, which is you should have received an announcement already regarding exam 3 assignment. So this is basically a fake assignment put in place so that you can use it on Carmen to play around with scores. I know some of you have contacted us about that, and so that has been uploaded. The scores have also been appropriately weighted in terms of homework, exam 1, exam 2, exam 3 in Carmen. The score to letter grade scheme has also always been there, so that has not changed. So that would be accurate to our score to letter grade scheme that's on the syllabus. That's also on Carmen, in case there's a question about that. Once again, the April 17th Pass No Pass deadline is approaching, and I mentioned this in the previous recent lectures because we've received some questions about it. And while we can discuss strategies about approaching this class and using the different resources that are available through Carmen, office hours, recitation, things like that, we can't specifically comment on any decisions regarding your major. That would be best done in consultation with your undergrad advisor. I know I may sound like a broken record at this point, but we don't want to push off any guidance or anything like that. I think it would be a disservice to you if we actually said anything definitive. So, because it warrants a much longer and more in-depth discussion than what we can provide. So that's my 2 cents on that. Okay, so let us go back now to just finish the last part of optical properties before we move on to composites. Okay. Okay. Well, interesting. Okay. So where we left off was the operation of the laser, and I skipped past cathodoluminescence due to time, but I will revisit it right now. So there are different ways one can use optical properties of materials for a variety of applications. Something that we've experienced quite a bit of, in terms of manipulating the optical properties of materials to get different colors in viewing devices like TVs, computer monitors has been the cathode ray tube, in which there's a material within the tube that's called a phosphor material. So what happens is these materials will be bombarded with electrons, and you can see different colors due to the different excitations within that material. And it's been quite useful to excite, different greens, different reds, different blues, RGB color to then get the desired viewing color. And that's also been quite useful as a characterization technique to understand how semiconductor devices have been fabricated, because the way, let's say, some sort of semiconductor layered device has been fabricated in terms of its composition, the different layers that have been constructed. You can characterize how uniform and how crystalline those layers have been, and also the composition by using cathodoluminescence. And so some of the examples that you see here involve, if you want to see an emitted blue color, you might use zinc sulfide. Here, zinc, cadmium sulfide plus some copper and aluminum dopants will be emitted as green. So you'll see a green color. This has actually been quite useful in transmission electron microscopy, because one of the ways we can see where the nanoparticles are in the microscope before we start to image with an electronic detector is using a phosphorus screen just to center the material. So if any of you have done characterization, electron microscopy, the green screen that you see is just zinc sulfide with some dopants. And then of course, if we want to tune red, you could see here an example of yttrium oxysulfide with some dopant concentration with europium. But note that, of course, this is incoherent, right? That means the light that's emitted is not in phase. When it is in phase, we see the application of lasers where we can get concentrated power, where all the photons are traveling in the same direction and in phase with each other. So that's cathodoluminescence, and that can be integrated. This type of detector can be integrated in, let's say, scanning electron microscopes. And so you could do imaging as well as get quantitative optical spectroscopy information. It's quite useful for the semiconductor industry. The other thing I wanted to mention is other applications of lasers. So we talked about semiconductor lasers. Of course, we all know, the compact discs, that used to be a thing. So CD players, if your computer still has an area, space for putting in a CD player, that uses red light. And then we had Blu-rays where you can have a blue laser and that will read and write the onto your compact disc. So that's the distinction between like a typical CD player and also, like a Blu-ray type laser. Is just different wavelengths. Blue has been difficult to access in terms of wavelength. And so, Suji Nakamura received the Nobel Prize for specifically just that, discovering a semiconductor that can do that. So gallium nitride, amongst others, type of compositions. So there's that. And in terms of, lasers that we experience every day, obviously there's lab grade, there's industry grade where it's very high power for, shock peening, laser shock peening to, induce compressive stresses so that you can strengthen the material that way at the surface. There's also everyday laser that we experience, right? We use red laser pointers. So that's just generating a red laser, and it's very low power. It's like milliwatts so that, you don't burn your eyes. And if you have a green laser, that's really just a red laser so you excite with a 808 nanometer wavelength, and then that goes through some sort of crystal, sometimes YAG, sometimes neodymium with some yttria type of crystal. And then once that incoming light impinges on that crystal, what you end up getting is actually a 1064 nanometer wavelength that's emitted. So that's near infrared, but you don't see that. You see a green laser because 532 is a second harmonic of 1064. You don't see the infrared 1064 nanometers, but you see the second harmonic, which is 532, which is why you get then that's how you make a green laser. And then there's some optics within the laser pointer that spreads the beam, so it's not as concentrated, and also you could see a little bit better than a little speck on somebody's PowerPoint presentation. So those are the more typical lasers that we experience day in, day out. There are also other applications where we can make use of how we can excite electrons, make a exciton, right? Electron hole pair, separate that exciton so that electrons go one way, holes go the other way. And of course, if electrons are all traveling coherently or in the same direction, then basically we have electrical conduction. Right? And so that's basically the premise of photovoltaic cells, solar cells, where we can excite a material like silicon, what we talked about, amorphous silicon, crystalline silicon, heterojunctions, where you have different layers of compound semiconductors like gallium arsenide, and then other layers like amorphous silicon or amorphous, and then crystalline silicon and all that. So you can make a whole stack to make your solar cell more efficient. But basically what you really want to do is be able to excite a wide range of utilize a wide range of wavelengths and make your cell more efficient, as opposed to having one type of material and then it's sort of locked in on one type of, one efficiency, and that's the Shockley quasar limiting efficiency. So here you see an example of organic light emitting diodes. You can also just have regular inorganic light emitting diodes, so that's just LEDs. And so what the stack that you see here is, you can see here you have one layer that's, let's say, N-type, one layer that's P-type, And then you have, you connect them, this stack in a circuit. And when you apply, you know, some voltage, you can drive the electrons from one side to another. And when you have here a PN junction, when you have a combination, you can, the combination of the electron hole pair, you can actually have some light that's emitted, hence light emitting diode, right? The other way is you can still have a PN type junction, but there the incident light that comes in creates the electron hole pair. And then when you drive, you know, the electrons one way and holes the other way, then you have electrical conduction, which of course is the premise of how solar cells work. Then the last part on optical properties is optical fibers. And of course, that's how the internet is the internet. I mean, that's how we have access to information, really. And it's through fiber optics, fiber optic communications, where information is sent through pulses of light. So the typical fiber optic cable that you see here is that you have some core, some cladding material that's outside, and then a coating to protect everything. And this relies on the index of refraction of the two materials, where you have a higher index of refraction in the core material, and then the outside is lower index of refraction, and you can cause total internal reflectance that you see here. So you could see that there's total internal reflectance where you don't have signal attenuation. So whatever photons that you send in, you will not lose it as much. And the attenuation rate is like 0.9925 out of 1, or 0.99 something something out of 1. It's extremely high. So very low attenuation of your signal. And then what comes out looks something like this, right? So if you send in an impulse signal, the output signal sort of looks like this. So there could be, you know, a spread, but it's not that much where you lose that information. And if you put all of these fibers, you know, parallel to one another, then you can send a lot of pulses all at once, right? And the typical fibers are, you know, like 10 micrometers in diameter. They're not that big. And so you can pack a lot of information in, and your signal is not attenuated all that much. And we can ask ourselves, well, you know, how efficient can this type of material be if you have to design something that will, let's say that has to go across like 16 kilometers, right? So your cable is extremely long, and you have this transmissivity of 0.9925. So here we're treating as, you know, here's the cable, and you're looking, you know, you're putting in something I naught, your incident intensity. You're asking yourself, okay, well, how efficient is it? Your transmitted signal is 0.09925, right? So what we're saying is the transmitted divided by the incident is 0.9925, and we want to know what the absorption coefficient is for this glass fiber in this type of cable over 16 kilometers. So if we know what we're solving for is the absorption coefficient, right? And so then if we take the log of both sides, the natural log of both sides, we take the exponent out. And so then beta, the absorption coefficient, is just ln of 0.9925 divided by the length, which is, let's say 16. I'm going to convert kilometers into 16 because into millimeters, because I know it's going to be probably some really small number. And that's going to be 4.71 times 10 to the negative 10 inverse millimeters, right? Because exponential of this needs to be unitless. So the units check out. So that's an extremely small number. we should also note that here it's going across 16 kilometers, right? This type of transmissivity values that you see, the fraction of transmittance, the attenuation, this number is more comparable to if you have a pane of glass that's like an inch, the power that if you shine, that incident light through an inch of glass and what comes out, that's about 0.9925. But that's for 1 inch of glass. That's an equivalent transmissivity. So for you to have the same amount of transmissivity over 16 kilometers is really high total internal reflectance and very low attenuation. So that's really impressive, right? So, all right, so we're gonna wrap this up before we move on to composites, right? So in summary, we talked about light in which and how it interacts with different materials like metals, semiconductors, insulators, and so how it can be reflected, absorbed, transmitted. We talked about the properties such as transparency, translucent, material can be translucent, opaque because of the crystallinity in a material, and also the electronic properties of a material. We talked about band gaps and how you need a photon with equal energy or higher energy than that of the band gap to excite an electron from the valence band to the conduction band. And we also talked about different applications in different devices that make use of luminescence, photoconductivity, applications like LEDs, solar cells, lasers, laser pointers, and also optical fibers. Okay, so with that, I'm going to switch over to the next module. Okay, oh, wrong one. Should be this one. Let's share that. Okay. Let's see. Ah, there we go. Okay. Okay, so we've wrapped up electronic properties, magnetic properties, and optical properties. Now we're going to bring it together to talk about composites. And so when we talk about composites, we have to define them and classify them in different ways because different materials will, of course, have different properties. And of course, composites will also have different properties based on the materials that you select. And of course, why would we bother with composites unless there's some advantages? And so what are those advantages? Is there enhanced mechanical strength? Is there enhanced resistance to corrosion, fatigue, things like that, which of course corrosion and fatigue will go way more in depth in the next 2 weeks. And how do we predict all these behaviors when we employ things like the rules of mixture? So we'll talk about that. Is it a linear combination and weighted averages of the different properties of your materials? What are the upper bounds? What are the lower bounds? What are the ranges of these properties within the composites? All right, so when we talk about composites, we're talking about synthetic materials. They're synthetic, obviously there are naturally made composites as well. We'll talk about that, but here we're really going to talk about the more synthetic composites. And it's really just a combination of 2 or more individuals, right, constituents in the composite. And our design goal typically is to obtain a more desirable combination of the properties, right? So either we want lower density or increasing strength or something like that. And of course, the prevalence of these composites are everywhere now, right? Here you see an example of a Boeing plane where there's a breakdown of the different types of materials within the plane. So here you could see, 10% of this plane is made of steel, 15% is made of titanium, 20% aluminum, and you could see the different color schemes here and where these materials are used. And then 50%, so half of the materials on this plane is just advanced composites. So carbon fiber, different types of composite, carbon fiber reinforced composites. So just different types of composite, and we'll go in depth as to what those composites are. In other applications, right here you see this turbine where you can have ceramic matrix composites, CMCs, that's used in the blades. There's also nanocomposites that, you know, are in everyday household items like tennis balls, where you can have a polymer, nanopolymer matrix that will, these particulates will impede the air from escaping. So once you open the container with, you know, the 3 Wilson balls, or, you know, whatever brand of choice, you know, air, you're going to start losing air from these balls, and they're going to deflate over time. But the nanocomposite liner will help retain that air for a much longer period of time than if you didn't have the nanocomposite lining there. Okay, so let's go into terminology and classification. So in a composite, you have multi-phase, and it's artificially made. We typically talk about the matrix of a material, right? And also then, you know, this continuous matrix that you see here. And then we also talk about the dispersed phase. That's the reinforcement. Like, why would you want to add this filler, right? So, and that filler can be in terms of fibers, it can be in terms of particulates. And when we talk about fibers, we have to talk about, you know, is it a continuous type fiber? Is it discontinuous? Are they chopped? Are they aligned? Are they not aligned? Are they randomly aligned? So those are all the types of descriptors of a composite. And so what can make up of these materials in the matrix and also in the dispersed phase, or the reinforcement that you're adding, the fillers that you're adding? Well, anything and everything, right? You can have metal, polymer, ceramic matrix. You can also have metal, polymer, ceramic fillers as well. And you can have different permutations of those combinations, but really the mixture is going to be something useful or enhanced in the end in terms of properties. Even though we're going to talk about, you know, artificially made composite much more, we've talked about some of the natural composites that are out there already, right? So when we were talking about polymers and how cellulose is a polymer in a composite, here cellulose, you know, is the composite, and it sits in, so you see that here, it sits in this these blue hemicellulose type of compound, and then it's all surrounded by a matrix of lignin. So that makes up wood, which is a natural composite. We also talked about, in the mechanical properties module here, we talked about how you can have bone, which is the stiffer material, right? Its modulus of elasticity is much higher than that of the matrix tendon, but the composite gives you strength and also ductility that you see here. And my laser pointer has gone away. Okay, here we go. So here the bone is much stiffer, and tendon has higher, greater ductility, right? And the combination of the two helps you be both tougher and stiffer, some combination, versus just obviously having tendon versus just bones. All right, so the matrix phase, the purpose of having that is that it can then transfer the stress. So if you're experiencing higher stress than what matrix can handle, that stress will be transferred to the dispersed phase, the reinforcement that you're adding, right? And it also surrounds your reinforcement. So it protects your material from the dispersed phase from the environment, right? And the different types of matrices that you can have, metal matrices, ceramic matrix, polymer matrix, composite, and your dispersed phase should have enhanced properties like increasing yield strength, tensile strength, creep resistance. We'll talk about creep when we talk about failure. It should also increase other fatigue, fracture toughness. So we'll talk about that as well when we talk about the failure analysis. In terms of polymer matrix composites, The dispersed phase should increase, have higher modulus of elasticity, higher yield strength, tensile strength, creep resistance. And the type of dispersed phases that you can have are particles, fibers, and other structural type of combination. And so here you see some examples of some woven fibers. Here's the cross section of how the fibers are integrated in with the matrix, right? So here are the long fibers that you see in the woven fiber. So here is the overall classification scheme, right? You have composites. We'll talk about particle reinforced, fiber reinforced, and structural type of composites. Within particle reinforced composites, we will start off with large particles, reinforcements, as well as dispersion strengthened types of composites. And then of course, we'll go into great detail for the others as well. So let's start with large particle composites. I'm going to pause right here because I see a question. What does the variable K stand for? Yeah, so that we'll talk about when we talk about K1C, when we talk about fatigue and failure analysis. We haven't actually covered that yet. Okay, so here we'll have some examples of concrete in terms of using large particles in cement matrices. Then we'll talk about nanocomposites when we talk about dispersion strengthened type of particle reinforcements. And then we'll also talk about, here I just brought an example of directional reinforcement in laminates. All right, so particle reinforcements. Here are some examples. You can have a matrix of ferrite, so that's ductile. Usually the matrix is more ductile than the reinforcement. Your particles will then be, cementite like Fe3C, and so that's more brittle, but it's stronger. Here's another example of metal matrix. So cobalt, it's ductile, it's tough, but so the area under the stress strain curve is much higher than that of the particles, which are hard and brittle, but of course it has increased strength. Here's another example of automobile tires where the matrix is rubber, and you can add carbon particles. So it's called carbon black because there's little particles of carbon that will add a stiffness and increased strength to the rubber matrix. Another example that we'll go into next is concrete. So we talked a little bit about concrete when we were talking about sourcing materials very briefly early on in the class, and how actually cement as the matrix of concrete, there's a lot of engineering to be done where you can decrease the amount of CO2 that's emitted, a greenhouse gas that's emitted. And of course, concrete is everywhere, right, in our society. So engineering the efficiency in which we can make cement will vastly help with climate change and pollution. And in concrete, the particulates are sand and other particulates, other particulates. And so why you want two types of particulates is that sand can fill all the small voids, while their particulates are the reinforcements that are larger. So you can have a combination of small and large particulates in a matrix. And of course, the particulates are harder and stiffer than the matrix. So they'll help to restrain the reinforcements, is that it will restrain the movement of the matrix that are close to each particle, so that you don't have, dislocation, things like that. Although this is a ceramic and not a metal. Okay. So the reinforced concrete here, what you can also do, in addition to having sand filling the void of the gravel particles in a matrix of cement to make concrete, you can also reinforce it even more so by adding in rebars or remesh to increase the strength. And so what you can do there is you can pre-stress the concrete by putting in the rebar and remesh under tension during the setting of the concrete. And then the release of the tension after the setting has taken place will leave the material in a state of compression, and that will make it stronger. And so here, to fracture then the concrete, the applied tensile stress then has to exceed this compressive stress. You can also post tension. So what that means is you can tighten the nuts to here that you see here on either end to place the concrete under compression and make it stronger. So there's a variety of ways to increase the strength of concrete, which is a composite. In terms of, we talk about enhanced strength, enhanced, stiffness. When we talk about the modulus of elasticity, here we can think about it in terms of the rule of mixtures, right? So as I mentioned before, how do we determine what is the upper range and the lower range of, the upper bound and the lower bound of the range of the mechanical properties that you can get? So for the elastic modulus, it's really just here a linear combination, right? Where the modulus of your composite is just the modulus of your matrix times the volume fraction of the matrix within the composite, plus the modulus of your particles or your reinforcement, sometimes it's E sub R, times the volume fraction of the particles that you've added in, right? So if you added in 10% by volume, 30% by volume, right? So that's 0.3 here. So that's the volume fraction or the volume percent, right? The lower limit, which can be derived from the conditions we'll talk about, the iso stress conditions, you can see here, this is going to be the lower bound of your range. So the example for this data set here is tungsten particles in a copper matrix, right? So this is metal matrix composite. And so the types of, you can apply this rule of mixtures to other transport properties like electrical conductivity, thermal conductivity. So this is lowercase k. It doesn't, that's not the same k that was asked before in the chat, but that we've covered already, in thermal conductivity. Okay, so now we talk about dispersion strengthened particle reinforced composites. Oh, this is still here. For dispersion strengthened composites, these are much smaller particles. They're typically on the order of 100 nanometers in diameter. And the matrix will bear the major portion of the applied load, and the small dispersed particles will help to hinder the motion of dislocation, right? And so there, if you hinder, your smaller particle is hindering dislocation motion, then you're restricting plastic deformation, because that's how that's a mechanism of plastic deformation. And this will improve your mechanical properties such as yield strength, tensile strength, and hardness. So those are particles. Now let's move on to fiber reinforced composites. So you can have different lengths of fibers. So then we can talk about, okay, well, what's some critical length that makes it, a continuous a fiber versus a discontinuous or shorter fibers? Like, what is long and what is short, right? And we have a rule for that. And if you have discontinuous or shorter types of fibers in your matrix, are they going to be aligned? Are they going to be randomly oriented? And how does that affect the properties of your composites?
Quick question, Professor.
Oh, hello.
Hi.
Hi.
A couple slides ago on the rule of mixtures, the upper and lower bound.
Yeah.
What exactly does that mean? How does that come into play? Does that mean that the actual elastic modulus could be anywhere between those two values? Or how exactly does the upper and lower bound come into play?
Yeah, so I will get to that. That derivation will come in very shortly. Yeah, here we go. Yeah, so I was going to go through those derivations in just a little bit. but I can address your question now. So the upper bound is that your composite is experiencing isostrain. That means, right, so here's the strain of your matrix. Here's a strain of your fiber, and the applied load is in the same direction as alignment, right? So previous to slide 24, I would have talked about alignment, but take my word for it, the fibers are aligned. In the lower bound, you're experiencing isostress. So here the applied load is perpendicular to the alignment of your of the fibers in the reinforced state. So what do we mean by loading parallel? Your load is parallel to the fibers. So if you treat your material as something cartoonish with some spring constant here, right? What you see is you can have, if your material is experiencing the same amount of strain, so it's isostrain, right? Once you pull on this material, the fibers are aligned in the same direction, your matrix is surrounding it, and everything is your strain, the displacement in the atomic positions are the same, right? So that's isostrain. If you have that, then all the strain is going to be the same, but your stress then is a composite. Your stress is, the stress state in the fiber times the volume fraction of your fiber in your matrix or in your composite, plus the stress of the matrix, which will be different than that of your fiber, times the volume fraction of the matrix in the entire composite. So once again, if you're loading, 10% by volume, 20, 30, 40, 60% by volume fiber in your matrix, that is, going to be 0.1, for fiber. Let's say you load 60%, that would be 0.6. And then your matrix will be 0.4 by volume, okay? So your composite stress, the stress that's experienced by the composite, it's going to be that linear combination. So then the stiffness of the of your composite EC in the longitudinal direction, so that's the L, is just the linear combination of the moduli, okay? So same thing, so that's the rule of mixture. If it's in the same direction, you just apply that rule of mixture we were talking about. The composite strength, same thing, it's gonna just be the failure strength of your of the composite and times the volume fraction and plus the stress of the matrix at fiber failure times the volume fraction of your matrix in your composite. So what do all these terms mean? That would have been the previous slide, but I'm just brushing through it to answer your question directly in a timely manner. The lower bound, I'll go briefly over this. The lower bound is when your applied load is perpendicular to the alignment of your fibers here. So here you could see that now instead of this type of equivalent circuit, we have where the strain is going to be the same. Here it's going to be in sequential order. And so deriving this will get us the relationship where the modulus of your matrix and the modulus of your fiber, it's actually this relationship. So it's actually going to be much lower than if you were in the isostrain, your load is parallel versus your load is perpendicular to the alignment of your fibers.
All right, thanks.
Yep.
That makes sense.
Okay. All right. Sorry, you're coming. The sound that's coming in is a little bit weak for whatever reason, and I'm pretty sure. Well, let's see. I've increased the volume quite a bit, so maybe that was the problem. Okay. But we'll get to all of this derivation. Right, Tio. We're talking about continuous. Let's go back to continuous aligned fibers in your composite. what does that really mean? There's going to be some critical length. And if the length of your fiber is much greater than some critical length that we'll talk about, then we call that continuous. Even more so, we tend to say if the length of your fiber is about 15 times the length of the critical length, then that's a continuous, we call that a continuous fiber reinforced aligned composite. So these, why would you want to add fibers, right? So they're very strong in tension. So that means they'll provide significant strength improvement to the composite. What you typically experience is, fiberglass. That's continuous glass filament in a polymer matrix. So we can see in this case, the glass fibers will increase strength and add a higher stiffness, while the polymer matrix holds all the fibers in place and protects it from the environment, and will then transfer the load. So if the applied load is much greater than that of what the matrix can handle, it'll transfer that load over to the fiber, and then that will absorb the load. And it also helps to inhibit crack propagation by doing so. And of course, when we're selecting materials, we want the modulus of elasticity of the fiber to be much larger than that of the matrix, right? To enhance the properties of the composite. When we talk about fibers, we can further classify them into whiskers, fibers, and wires. And so with whiskers, these are typically thin single crystals. So there's a large length to diameter ratio, yes. So typical whiskers are, graphite, silicon nitride, silicon carbide. But of course, to make single crystal of these things, they're obviously expensive, and they can be hard to disperse. Whereas for fibers, they tend to be easier to make, less costly in terms of manufacturing. Their crystallinities, they're typically polycrystalline. They can even be amorphous. You can have fibers that are ceramics like e-glass, aramid, so that's your Kevlar, that's your Nomex, right? You can also have boron fibers, alumina fibers, what have you. For wires, they tend to be metals. You can pull out metals, and so they tend to be more like steel, molybdenum, tungsten. These are some examples of fibers that are in the wire type configuration. So let's look at the stress strain curve of the fiber as well as the matrix, and when will your composite fail or fracture. So here, the polymer matrix, as you could see, will will distribute the applied load to the fiber and inhibit the propagation, the crack propagation. So the matrix has to be more ductile, and so that we can see here, versus here you could see the fiber in red. The stress strain curve for the fiber in red is much less ductile. In fact, it's stronger, but it's quite brittle. So in stage 1, what will typically happen when your material is under stress, there's an applied load. You could see here in stage 1, that's the elastic region, right? And then when you go to stage 2, then the matrix takes over. Here's the average of the composite. The average stress strain curve for the composite is in green. So in stage 2, there will be some plastic deformation that's taken on by the matrix. But then up to a certain point here, you could see that there's going to be some failure, and that point will be the fracture, the point of fracture for the fiber, right? So that's where your composite is going to fail. But first, everything will deform elastically, and then there will be a stage 2 where the matrix will start to deform, plastically, and then up to the point where you experience fracture strain. That's when your composite is going to fail. So when we talk about the continuously aligned fiber, this is what cartoonishly it would look like. When the length of the fibers are shorter than that of the critical length, you can still have alignment, as you see here, but that's discontinuous. You can also have discontinuously aligned, fibers, but aligned in a random fashion here. So there's no alignment. When we talk about the alignment, aligned continuous fibers, you could see here some examples of, molybdenum, alpha molybdenum in, the nickel aluminum brittle fibers in a matrix of molybdenum that's more ductile here. You can also see here the alignment of silicon carbide glass fibers in this matrix here. When we talk about discontinuous fibers, right, it can be discontinuous and random in 2 dimensions. And so here is an example of carbon-carbon composite, where the carbon is the particle or the fiber and the carbon is also the matrix. You can also have carbon in polymer matrix, as you see here. So here, these chopped particles, these chopped fibers can be aligned in the 2D direction here. And they're very stiff and they're very strong, but then the carbon matrix is less stiff and less strong. And so the applications that, utilize this sort of carbon-carbon composite are disc brakes, gas turbine, exhaust traps, missile nose cones even. So there's quite a bit of usage for discontinuous fibers that are randomly oriented. And of course, here we see an example of the 2D alignment, but you can also have random in 3D as well. And they can also be aligned. Okay, so now let's talk about the critical fiber length for effective stiffening and strengthening. So if your fiber length is much larger than some critical length, what is that? Well, your critical length, you can calculate that by knowing the fiber's ultimate tensile strength, multiply by the diameter of that fiber, nanometers, micrometer length scale, divided by 2 times the shear strength of the fiber matrix interface. So there you kind of have to know the type of adhesion between your fiber as well as your polymer matrix to know the shear strength of that interface. So the interface is really important. We've been talking about all these composites, assuming that, once you make the composite, there's really no voids or, it's all one piece now when we talk about the composite. Obviously, if you don't engineer it very well, you can have non-interactions, you can have voids where, the particles aren't interacting or the fibers aren't interacting with your matrix, and thus then your composite is not as optimal as it could be. So here we talked about before, if for fiberglass, the common fiber length is typically longer than 15 millimeters. For the short, thick fibers, you could see here the strain fields, and it can be quite have lower efficiency. If you have longer fibers, then here you could see that the fiber takes on a lot of the load. And then when it's farther away, you could see here that there's distortions in the strain field. So let me pause here and see if there are any questions. Let me scroll back up a little bit. So the question is there yield strength and ultimate strength with composites in the same way there is for ductile materials, or are composites more like brittle materials with only an ultimate strength? Oh, I see. Before basically it fractures. Well, it's sort of some combination of the two. Okay, so let's go back to that. Yeah, here we go. Yeah, so what you experience here, right? I mean, it's an average of both the more ductile matrix and the brittle fiber. And so yes, you still have the same elastic region here, but then you have plastic deformation here. Okay. And there's another question about slide 21. LC on slide 14. Okay, let's go back to slide 14. Okay. Oh, I see. LC. Yeah, so this is, right. So this is the critical length of the fiber. And so if the length of your fiber is much greater than the critical length, we call that continuous. If it's typically, if it's 15 times the critical length, that's definitely continuous. If it's discontinuous, that just means it can be slightly greater, but not 15 times that, or it's less. The length is shorter than the critical length. Both could be discontinuous. Okay, let's see, where were we? Okay, so rule of mixture. Let's talk about that. So rule of mixture, we talked about how it can be applied in terms of the modulus of elasticity. We can also talk about the density. We can come up with an average density of the composite by just doing the linear combination of the fiber and the matrix. So as you recall, the density is just, all right, the weight of the material, that's grams divided by some volume. So that's, let's say, milliliters. And so we can rewrite this as the density times volume is equal to the weight, right? So then the composite weight is just the weight of the fiber plus the weight of the matrix, and thus the density times the volume of your composite. So the density of the composite times the volume of that composite is going to be just the linear combination of the density of the fiber times the volume fraction or the volume of the volume fraction of the fiber in the composite times the density of the matrix and the volume matrix, the volume fraction of the matrix, right? And so density is just VF, VC, volume of composite, plus sigma, density of matrix times the volume of the matrix divided by the volume of the composite. And so this is just the volume fraction. So once again, we see it's just a rule mixture. It's just some linear combination here where your density is weighted. Density of the composite is just the density of the fiber times the weighted averages based on the volume fraction. Thermal conductivity, same thing, right? Thermal conductivity of a composite is just the thermal conductivity of your fiber times the volume fraction. So if you see this, that's obviously the volume fraction. Sometimes what you'll also see is just this. This is an indication that it is the volume fraction of the fiber in the composite time plus the thermal conductivity of, right, of the matrix times the volume fraction. So in a simplified, okay, well, so we'll denote this as, this is the volume fraction. Or if you see something, sorry, this should be C. So if you see something like this, it's the same value, but now VM is the volume of the matrix versus volume of fiber. But either way, it's the volume fraction and it weighs the thermal conductivity contributions or the density contribution to then give you the overall thermal conductivity of your composite or the density of your composite. Okay, with that, we'll pick up here next time. All right, have a good weekend, everybody. See you.